In this episode, we're going to focus on a risk that sounds almost magical until you break it down: training data leakage. The concern is that sensitive information, like secrets or personal details, can end up in places it should never be and then show up later in outputs. Sometimes people imagine this as the model remembering a password like a human would. The reality is more practical and more preventable. Leakage usually happens because sensitive data was collected, stored, logged, shared, or reused in ways that made it accessible to systems that were not supposed to have it. If that sensitive data ends up in a training set, a fine-tuning set, a prompt history, or even an evaluation dataset, it can influence outputs in ways that are hard to predict. The goal for beginners is to learn what types of data are most dangerous, why tokenization and text processing can create unexpected side effects, and what habits and controls reduce the chance that secrets or PII end up embedded where they do not belong. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at Cyber.Author.me in the Bare Metal Study Guide series. Let's start with what we mean by secrets and PI, because those words get used broadly. A secret is any piece of information that grants access or privilege, like an API key, a password, a private encryption key, a session token, or a shared secret used between systems. Secrets are dangerous because they are directly actionable. If leaked, someone can use them to log in, impersonate a service, or decrypt data. PII is personally identifiable information, which includes things like full names, email addresses, phone numbers, government IDs, and sometimes combinations of details that can identify a person. PII is dangerous because it can harm individuals and create legal and compliance issues. In AI security, these two categories matter because they often appear in the same places you might want to use for training or evaluation, such as support tickets, chat transcripts, logs, and incident reports. A key mindset is that leakage is often a pipeline problem, not a model problem. Models do not magically pull secrets from nowhere. They reflect the data that was provided to them during training, fine-tuning, retrieval, or prompting. If your pipeline collects support transcripts for quality improvement, and those transcripts include customers sharing passwords, you now have a risk. If your developers paste real credentials into test prompts, you have a risk. If your logs record authorization headers, you have a risk. A big part of prevention is simply designing systems so that sensitive data is less likely to be present in the first place. This is where data minimization, access control, and redaction connect directly to AI safety. There is also an important difference between memorization and reconstruction. Memorization is when a model can repeat an exact string it has seen before, like a specific key. Reconstruction is when a model uses patterns to infer or regenerate something that is similar, like a typical-looking token format or a plausible email address. Both are bad if they create real exposure, but memorization is the more severe scenario because it can output the exact sensitive value. Memorization becomes more likely when the sensitive string appears many times in the data, is distinctive, and is associated with strong patterns that cause the model to reproduce it. For example, if the same secret appears repeatedly in training examples, the model may learn it as a frequent completion. This is one reason rotating secrets and avoiding reuse is helpful even outside AI. Repetition makes sensitive data stick. Now let's talk about tokenization side effects, because this is where beginner intuition can be misleading. Tokenization is the step where text is broken into pieces that the model uses internally. Those pieces are not always single letters or words. They can be chunks of characters, common word fragments, or other patterns. From a security perspective, tokenization matters because it can make certain strings easier or harder for the model to reproduce. A secret that matches common patterns, like a base 64, like string, might be tokenized into chunks that are easy to stitch back together. A long random secret might be broken into many tokens, which can reduce exact memorization but does not eliminate it. Tokenization can also create a false sense of safety. People sometimes assume that if a secret is long and random, it cannot leak. It is safer than a short, predictable secret, but if it is present in training data, it is still possible for it to appear later. The safest approach is to keep it out of training data entirely. Tokenization also creates side effects in redaction. If you attempt to redact sensitive information by removing certain patterns, you might miss variants because the text can be formatted in many ways. An email address might appear with extra punctuation. A key might be split across lines. A user might paste a credential with spaces or quotes. If your redaction relies on simple pattern matching, you may leave fragments behind. Those fragments can still be sensitive, especially if they can be combined with other context to reconstruct access. This is why redaction for AI pipelines often needs multiple layers, such as pattern-based detection, context-based detection, and conservative removal of high-risk fields. It is also why you should prefer structured sources where sensitive fields are separated, because structured separation makes redaction easier than guessing from free-form text. Another pipeline side effect is logging, which is an easy place for secrets and PII to leak. Many systems log requests for debugging, and those logs may include headers, tokens, user identifiers, or payloads. If those logs are later collected as training data or used in evaluations, you have unintentionally created a dataset full of sensitive material. This can happen even in well-intentioned environments, like development and testing, where people copy production-like data to reproduce issues. Prevention starts with deciding what you log and what you never log. A strong practice is to block logging of known sensitive fields and to mask or hash identifiers when needed for correlation. It also means treating log stores as sensitive systems, because they often contain more secrets than people realize. A practical prevention pattern is to apply secret scanning and PII detection before data is stored or shared. Many organizations use automated scanning tools that look for credential formats, private keys, and other known patterns. The important concept is not the specific tool, but the placement in the pipeline. You want scanning to happen early, before data enters long-lived storage or datasets used for training. If you only scan at the end, you may have already copied the data into backups, caches, and analytics systems. Early scanning supports early deletion or masking. It also supports the principle of least exposure, meaning the sensitive data is visible to as few systems as possible for as little time as possible. It is also important to learn the idea of dataset purpose. Data that is useful for troubleshooting might be dangerous for training. For example, a support transcript can teach your model how users describe problems, but it can also contain passwords, addresses, and payment details. A safer approach is to create purpose-built datasets where you remove or replace sensitive values and where you keep only the parts that actually teach the behavior you want. If you are training a model to classify ticket categories, you do not need the full raw message content with personal details. You need features that indicate the category, like keywords, symptoms, and product areas. Purpose-based dataset creation is one of the most effective ways to reduce leakage because it changes the default from collect everything to collect what is needed. Another subtle issue is that tokenization and model behavior can leak partial secrets, not just whole secrets. Even a fragment of a token can be sensitive if it can be combined with other information. For example, if a model outputs the first half of a key and a user already has the second half from another source, the secret is compromised. Models can also leak patterns that make secrets easier to guess, like revealing that a token starts with a certain prefix or that an account name follows a certain format. This is why you should treat any output that resembles a credential or contains identifiable personal details as high risk, even if it is incomplete. In safe designs, you apply output filters and detection to block suspected secrets and PII from being shown to users. Prevention is better, but output controls are a useful backstop. A strong operational habit is to assume that anything you put into a prompt can be stored somewhere, even if you believe it will not be used for training. Prompt logs can exist for debugging, monitoring, and quality improvements. Even if the model provider does not train on your data, your own systems might retain it. So the safest behavior is to never paste secrets into prompts, to never include full PII unless absolutely required, and to use placeholders or synthetic values when testing. Beginners sometimes treat prompts like private conversations, but in engineering, prompts are inputs to a system that may be recorded. When you adopt that mindset, you naturally reduce leakage risk. By the end of this episode, The big takeaway is that preventing training data leakage is mostly about controlling where sensitive data flows. Identify secrets and PII, reduce their presence at the source, scan and redact early, avoid logging sensitive fields, and build purpose-based datasets that contain only what you need. Understand that tokenization can make strings easier to reproduce and can complicate naive redaction, so you should not rely on string length or randomness as your main protection. Then add backstops like output filtering and review processes for high-risk workflows. When you do all of that, you are not relying on the model to be polite and forgetful. You are designing a pipeline where sensitive data simply has fewer chances to become part of the model's world in the first place.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.